let's go.
Check. Next up, we have Giulio from the CVD lab, and he will be telling us about LARLIB, a library for geometric and topological modeling.
Yeah. Hi, everybody. I'm Giulio. I'm a fellow researcher at the Università degli Studi di Roma 3 and at the Computational Design Visual Laboratory of Università degli Studi di Roma 3. And I'm here to present LARLIB.jl, which is the Giulio implementation of the linear algebraic representation. And this library has been partially founded by GeoWeb, which is a company run that's helpful for geometric modeling and stuff like that. And so what is the linear algebraic representation, which can be called LAR for friends? It's a representation scheme, essentially for geometric topological modeling. And the main concept is that the domain of the representation scheme is provided by d-dimensional cellular complexes, and they are linked together by a set of sparse matrices. So like you have a zero-dimensional cellular complex, and you have like the link in between the zero dimension and the first dimension with a sparse matrix, and so on with for the n dimension. But we care more about the third dimension. So, and everything on LAR is based with very basic linear algebra operation, like the sparse matrix vector multiplication. And by these simple premises, we can do practically everything. And we choose LAR because it can scale very well, and most of the algorithms are like embarrassingly parallel. And so it's very good also because it can handle very well like non-manifold geometries, and it can be also treats well even stuff of higher dimension. Well, now let's talk about LARLIB. LARLIB, it's, as I said, the Julia implementation. And why we did choose Julia? Well, I said to you that it's based on an algebraic multiplications and stuff like that, and Julia is very good for that, especially for the built-in type of the sparse matrices. And also it's very good with parallelization. And also it's good for us engineers because it has good stuff like Travis, Coverall, and just a good environment for developing stuff. Also we use a lot of third parties, libraries like packages like, as everyone uses Julia, so yeah. So what are the features that LARLIB implements right now? The first of all is the arrangement of cellular complexes. Arrangement is like, can be seen by simplifying like the Boolean union between models. And we can do parametric geometric modeling, and we can integrate over solids and surfaces, and we get a lot of utilities and stuff for geometric modeling in general, like find if a point is in a face and stuff like that. For example, some stuff. Okay, this is the planar arrangement. It means that this is the, on the bottom there is the signature, but like we can see the input that is just this model over here, that's just the points, and EV is the sparse matrix between the zero dimension, the one of the vertices, and the one dimension, that one of the edges. And so we got practically this is just a bunch of edges, just a soup of edges. And from that we can create faces, 2D faces from that. And this is an exploded visualization of this one. So we can see every kind of face that can create from that. And like we can see like non-convex faces like this one, and are handled very well by stuff like LAR. And this is more explanation of the planar arrangement. These are the steps, like the input edges. In red, we can see like here we, if you see like there is an optional argument called sigma. That's the red phase. It means that you need to fragment everything that's in the area of sigma. So we got like, these are the edges, here are fragmented, and then the useless edges are deleted because they are outside the sigma area, and then are created the faces. Also note here that faces number 1 is practically a hole in phase number 2. Phase number 2 as a whole, let's say that. And it's LAR as a native support of this kind of things. And the spatial arrangement is the same stuff, but in 3D. Like we can see this example where the signature is not visible. Yeah, it's the same stuff, but we add also a new matrix for the relation between edges and faces. And so we got a 3D model, let's say that. And this is the spatial arrangement, so the Boolean union between 2 cubes made of, each cube made of 10 times 10 times 10 little cubes. So it arranges that. And the spatial arrangement, the steps are like this, that we consider each face in a separate fashion. And like, for example, let's focus on the red one. We got the red one, and we got the blue ones that are the one which are near to the red one. And we consider the edges of the red one and the edges that are created by the intersection of the blue ones with the plane of the red one. And we do the planar arrangement. And we repeat from step C to G for every phase in the complex, on the cellular complex. And we got the full arrangement of the 2 models. And this is for like assemblies of model or like parametric geometric modeling. Like we can do hierarchies of models, like this one. Like we can compose basic stuff with a few instructions and do like basic operation using CAD and CAD. And this is another stuff that LAR can do. Like we can extract stuff from bioimages. Like we got a scan of biotissue, and we can use like neural networks to classify the stuff in the scan and give those stuff here in input as LARLib, and it will give us a LAR model, which is a very compact version of a 3D model that can handle practically anything. And this, for example, is an extraction of a bone. This is a scan of a bone, and this is the 3D model that has been simplified by LAR. And it was at the beginning just a bunch of voxels, a lot of voxels, and here has been simplified by LAR and can be seen real time with on OpenGL visualizer without problem. And what's in the future of LARLib? Well, first of all, we need to implement the rest of the Boolean operations, so difference intersection. And also, we want to extend the parallelism because the arrangement algorithm has been parallelized because, as I said, it's embarrassingly parallel. But we want to do that, to port that also on GPU because GPUs, you know. And we want also to extend the utilities like the import-export, because right now we can import and export from only OBJs and stuff like that, and also extend the topic on bioimaging, because we think that's a good stuff and we should work on that more. So I'm done, so thank you all for attention and interest. I think that we got 1 minute or 2 for questions. Well,
time for one question.
Yeah, the model is like, it's impossible to explain LAR in like only 10 minutes, but it's a very, very intelligent stuff with a lot of very intelligent algorithm behind, and that's very mathematical. So if someone is interested in LAR and stuff like that, I can explain with a piece of paper, okay, because with a presentation it's really hard. But thank you all anyway.
All right, thank you.